Hello. Let's begin our recording for the topics this week. In this video, we have the following goal: the extremal functions of several variables. We will do the first topic only. I will leave the topic on absolute maximum value and absolute minimum value over some bounded region as supplementary material. So it's not part of the exercise. But it's nice if you study them. And the next topic will be Lagrange multipliers. Here in these topics, both of them, we're getting the extrema or like the maximum or minimum. The first one is on somewhat unconstrained, and then the other one we have a function and we want to get the maximum and minimum subject to some constraints. Why it's also called Lagrange method for or Lagrange multipliers or constrained optimization. So last time on one of the sections I have I ended with tangent planes and normal lines up to the example that we have. And in the other section, I haven't done thoroughly the example. So now let me begin this recording by showing you the example. So we have on tangent planes and normal lines. So let us consider this example. Suppose that you have a surface S defined by z is equal to 6 minus x squared minus y squared. Then the goal is to find the tangent plane, the equation of the tangent plane at the point given by 1, 2, 1. Tangent plane of our surface S. Okay, so let's do. So first is we have to express S as f x y z equal to 0. So your f of x y z here is given by x y z. We can, as I mentioned before, we can put this z at the other side or put everything here at the other side. It will not be very relevant because you can divide everything by negatives or something like that. So here I will choose to put this x squared plus y squared plus z minus 6. This is equal to 0. So this one is our surface S equal to 0. So this is the equation of our S in this form. Now, to get the normal vector, we get the gradient of our f at the point, this point. So first, we are going to get the gradient for an arbitrary point x, y, z. So this is just f sub x, f sub y, not small f, but rather big F. F x, f y, f z. So we get the partial derivatives. With respect to x, we get 2x. With respect to y, we get 2y. And with respect to z, we get 1. Now, if you get the gradient at the point 1 to 1, you get 2, 4, and 1. This is our normal vector. Now, for the plane, omega, this is the plane tangent to S at point 1 to 1 is given by, this is our normal vector. So this is just 2, x minus 1 plus 4 y minus minus 4. Oh, wait. Minus, so this is our point, minus 2. And then lastly, plus z, 1 times z minus 1. This is equal to 0. So this now is your standard equation. So to get the general equation, you get 2x plus 4y plus z, and then minus 2 minus 8 minus 1 equal to 0. So get 2x plus 4y plus z minus 11, or is equal to 11, or it depends on how you represent. So this is now the standard equation. Okay, let me put it this way. Minus 11 is equal to 0. So here we get the general equation of our tangent plane omega. Of course, this omega is just the name of the plane. Now, if you are to ask what is the equation of the normal line to S at the point P, given when 1 to 1. So the equation here, we get first the parametric. Parametric equation is given by L is X, Y, Z. Get the first, the point given, it's just 1 to 1, and then plus our ABC. So ABC is 2, 4, 1, and then T here, where T is a real number. And then if you get the symmetric equation, we get x minus 1 over 2 is equal to y minus 2 over 4 is equal to z minus 1 over 1. So this is your symmetric and parametric equation of the normal line to S at the point P. So in this, if you have this S here, this is our portion of our surface. Then suppose this is the point P. This is your normal line. And then this is your omega that we have solved above. All right. So feel free to pause the video before we will go to the next topic. Okay, so the next topic is extrema of functions of several variables. I will be drawing some graph here, but in this case, my several means 2. So suppose we get some graph of a surface. Here is our surface. Then there's some hole. Then some hole here. So here, if we get these points, these are called this A1, A2, A3. They are called relative maximum. And here, B1, B2, and B3, they are called relative minimum. Minimum. Okay. So why? Because as we have in the previous discussion, so over some small region, the A is the A here, which is a function of some xi, is the greatest. So suppose this is your z, and then this is z-axis. This is your corresponding points. Over is the greatest, and that small region, in this case, the small region is, suppose this is just the small region in the xy plane. So here is the function value of a. Here, a1 is the greatest, f of xi. Suppose this is xi, yi. In this small region, the function value is the greatest. In the same way, over some small region or small neighborhood, or like over small region in the xy plane, your b1, which is the function value of x, say j, y sub j, is the great, in this case, lowest in that small region. Suppose this is the small region in that. So that's how we view relative extrema and relative minima. You can actually look at the drawing in our module. All right. Now we go to the first derivative test. All right. So here, if the function is defined in some region centered at this x o y sub 0, and f as relative extremum. Let me go back here. So this relative and maximum and minima are called relative extrema in general. So as we have in Math 27. You have a relative extremum at this point x0, y0. Then what can you say? Then if our f and f sub y exist, then your this partial derivative evaluated at that point is equal to 0, and also your partial derivative with respect to y evaluated at that point is also equal to 0. Okay, so a remark, these are the points here satisfying this one are called critical points. So here x0, y0 is a critical point if the following are true. Number one, f sub x at that point is equal to 0, and also the partial derivative at that point with respect to y is equal to 0, or your ones of the following is true. So either the partial derivative at that point is 0. So here is either the partial derivatives are 0 or one of them does not exist. Does not exist. Walang S. Okay, so let's do an example. So here, example, we will use this example later on when we do second derivative test. So find the critical point of this function. X squared plus y squared minus 6x squared plus 6y is minus 1. So solution, first we get the partial derivative with respect to x. So this is just 3x squared minus 12x. Then we equate that to 0. Therefore, factor out x, we get, and we can factor out x, and also we can factor out 3. So we get x minus 4 equal to 0. This means x is either 0 or x is equal to 4. So that one. And if we get the partial derivative with respect to y, this is 2y plus 6. So here we get 2y 6. And then if we get equate this to 0, this implies that 2y plus 3 is equal to 0, which means that y is equal to negative 3. In this case, we pair them. So we have critical points are the following. So we have 0, and then we have 4, and then partner is negative 3 and negative 3. All right, that's it. These are the critical points. Example number 2. We get g given by e raised to xy. So what are the critical points? So g sub x is equal to y, e raised to xy. If we equate this to 0, this implies that y is 0, because this part here can't be 0. And then g sub y, with this is just x, e raised to xy. Equating this to 0, this implies that x is equal to 0. Thus, in this case, the critical point is just 0, 0. This is the only critical point. Now we get a slight challenging example wherein we do cases. All right. So here we get h given by x raised to 3 minus 3x squared y minus y squared. So we need the critical points. Critical points are blank. So we get the partial derivative with respect to x. So here, with respect to x, we have 3x squared minus 6xy. Then we equate that to 0. This will imply that 3x and then x minus 2y is equal to 0. This will imply that x is equal to 0 or x is equal to 2y. So we have two cases here. And also, if we get the partial derivative with respect to y, we get negative 3x squared minus 2y. Equating this to 0, we will use this later. So first, we will have the case 1, which is x is equal to 0. When x is equal to 0, what can you say? So we use this equation here. So negative 3x squared minus 2y is equal to 0. So we get negative 2y, negative 3 times 0 squared is equal to 0. That means negative 2y is 0, so y here is equal to 0. So you have one critical point. CP is 1 CP. Okay, let me write it properly. Critical point I will abbreviate as CP. CP1 is 0, 0. Okay, we have 0, 0 is a critical point. Now, we go to case number 2. Case number 2 is x is equal to 2y. All right, we will substitute this negative 3 times 2y squared minus 2y is equal to 0. Here we get negative 3 and then 4y squared minus 2y is equal to 0. And what? We get negative 12y squared minus 2y is equal to 0. Here we get y and then 2 and then negative. And then we get 6y plus 1 is equal to 0. All right. Here, y is 0 or y is negative 1 over 6. So here we have case 2.1 and then case 2.2. So here for case 2.1, we get y is equal to 0. When y is equal to 0, then we will substitute our equation here. So x is equal to 2y. That means x is equal to 2 times 0. Here we get 0. So we get the same critical point CP1, which is just 0, 0. But they are the same, but here and here. Now, we have case 2.2. When y is equal to negative 1 over 6, x is equal to 2, it's negative 1 over 6, we get a negative 2 over 6 or negative 1 over 3. So we get the CP2 given by x is negative 1/3 and then y is negative 1 over 6. Overall, the critical points are those we have collected. So the first is 0, 0, and the other one is negative 1/3 and negative 1, 6. So here is our critical points. So the second one, the next thing that we have done in Math 27, if we get critical points, is what are the value at this critical point? Whether is the function relative max or minimum at those critical points. At those critical points. Okay, so here we will use our second derivative test. So the second derivative test is as follows. So this is the second derivative test. Okay, second derivative test. So this is the statement. So here we get f, function of two variables x and y, and f sub x and f sub y, and also the second partial derivatives. So here we get fxx, fyy, and then fxy are continuous on some region containing the point x0, y0. And then here And also, your f sub x evaluated at x0, y0 is equal to 0, and f sub y evaluated at x0, y0 is equal to 0, we will define your, here we have d of AB. This is like Hessian, but anyway, let's just call this the uh, d of AB Hessian. I don't know. Let me let me check the literature. Here we get what is this? Let's just call this the d value. Yeah, some books call this Hessian, but it's not very used in all the books. For example, here in Stewart, it's not using that term. In the module, it's not also using that term, but in the slides before, it's called the Hessian of our f at the point AB. Okay, let's just call this DAB. So this is just something like the determinant of this x, x, f, y, y, and f, x, yx, and then f, x, y. So this is for easy recall. So this, just multiply this and recall that fxy is equal to f yx. So here we get fxx at AB, then fyy AB minus fxy at AB, and then you square this. Okay, you square this last term here. So this is just this times this. So it's like multiplying by itself. And then we have the following conclusion. First is f has relative minimum value at this point AB if your d at AB is greater than 0 and fxx at AB is also greater than 0. See, this is always negative in relative and relative extreme. The second one is f has relative max at AB if your DAB is greater than 0 and your fxx at AB is less than 0. The other one is f as a saddle point. When we say saddle point at AB, I'll define later if your D at AB is negative. And then the saddle point is so it's neither max or min, neither relative max or relative minimum. Here, a saddle point, let me state what is. It's a critical point of a function where the first partial derivatives are 0. And it's not a local or a relative maximum and relative minimum. If you have, it derives its name from the word saddle. So for example, you get this as your graph of this function. So here is the saddle point. So one characteristic of this point is the partial derivatives, the first order partial derivative here is 0. Okay, so it's like the saddle of a horse. This is why it's called saddle point. This is familiar to you, like before in quadric surfaces. And the fourth conclusion is no conclusion actually. The test is inconclusive if your D at that point AB is 0. All right. Let's apply this to our third example. So in this third example, you could actually, where should I apply? Okay. Okay, let's apply this in the first example. Suppose we get the first example. So the first example is this f and x3 plus y2 minus 6x squared plus 6y minus 1. So this previous example. So we have the critical point are 0, 0, and 4, -3. Now, what is the what happens to these critical points? So we will do the D. We will inspect D. So first we get a table. And then at this table, we get 0, 0, and then 4, -3. The first column, we have this f sub xx. So your f sub xx here, okay, let me make some space. So your f sub xx at arbitrary xy is 6x minus 12. F sub y is earlier, so we get 2. And then f sub xy. So here, let me do the rotation here. So f sub x is 3x squared minus 12x. So here f sub xx is 6x minus 12. So f sub y is, what is that? 2y plus 6. And then f sub y is just 2. And f sub xy is just this. We take the derivative with respect to y, it's just 2. Here 2. And then if we evaluate at 0, so 6 times 0 minus 12 is just minus 12. And here 6 times 4 minus, here we get 6 times 4 minus 12. So we get 12. So this is our part here. Okay, for this column, we get 2, 2, we get 2, 2. And then here, of course, they are the same. So we have D. D is just, for the first one, we get this multiplied by this minus square of this. So here we get 12, okay. 2 times 6x minus 12 minus 4. So we get 12x minus 24. Oh, wait. So f sub xy is actually here we get the partial derivative with respect to x, and then with respect to y we get here 0, 0, 0. So this with respect to x we get 0. Okay, just pause this if there's a lot happening, and then so it take it slowly so that this is the 0, 1. This is just 2. This is 0 here. Now, if you plug in 0, 0, here we get negative 24, and here we get 12 times 4, and then minus 24. So here we have positive 24. Because 12 times 4 is 48 minus 24. So, okay, let me write that out so that it will not be. So here we get this 0, 12 times 0 minus 24. So you get negative 24. Here we get 12 times 4 minus 24. So we get positive 24. So the conclusion is F has a saddle point at 0, 0. And then the saddle point is given by, which is 0, 0, and then f of 0, 0. So f of 0, 0 is just 0, 0. If you plug in 0, 0 here, you get oh, wait. It's not, what did we get before? So here, for the first example, oh, 0, negative 3. So I have a mistake. So let me clarify that mistake. So instead of 0, 0, I have 0, negative 3. And everything is okay. So here is 0, negative 3. So if you plug in negative 3, you get 0 and then negative 10. And then f has, this is positive, but fxx is positive. So here has relative, pag positive, minimum value at the point for negative 3. So I will be checking this part here, saddle point and relative minimum. Here, I'm not particular with the function value because sometimes it's like a very long function and then it's hard to get the function value. In fact, the relative minimum is given by this is just f of 4, negative 3. And again, as I mentioned, this is long. So here we get 4 raised to 3 plus negative 3 squared plus 6 times 4 squared plus 6 times negative 3 minus 1 is just negative 42. So here we get the relative minimum is negative 42. And again, as I mentioned, I will just check whether it's this part here in case it's asked in the problem. All right, so I think that's all for our partial second derivative test. Now, I mentioned earlier that regarding the absolute maximum and minimum, Uh, I will leave this as supplementary readings. So in that case, I will um, let you do this as your extra reading time. But I'm assuring you that it's not part of your examinable work. So it's not on the exercise and on the exam. So now you can pause this video again and also um mm, yeah, pause the video and rest before going to the next topic on Lagrange multipliers. All right. Now I'll do the Lagrange. I'll just state the method. I will not be doing the derivation. So here the situation is you get the situation here is this is for constraint optimization. So what we are given is want to optimize a function, and then we have say f, and then given constraint g of xy is equal to some uh, let me call this 0. Uh, yeah, this is so this is our constraint, and then this is the function that we want to optimize. So as a warning, here in the method that I will be using, I'll use the method in the book by Stewart instead of the method in the module. So how do you find the the maximum and minimum value? So this is the method of Lagrange multipliers. So first step, given objective function f of x, y, or z, or maybe just f of two variables, and then constraint. The constraint is given by g of x, y, z is equal to some constant k, or maybe some function of two variables is equal to k, or you can put the k at the other side and then 0 at the other side. Doesn't matter a lot because derivative of constant is 0. The first step is so here we have the we have the assumption that extreme values exist, and the gradient of g is not 0. So here we will, the first step, assuming the nice conditions. Here, the gradient of g is not 0, and extreme values exist. Actually, this is just some things that will be careful, but in the computation is just this. So first is you have to find the x, y, z such that your del f is equal to lambda gradient of G. So here, this is our lambda. So this is the, so maybe for the Lagrange multiplier. And then after that set, the first step, we get the value. Evaluate your F at the X, Y, and Z from your A. So the maximum is the largest, and then the minimum is, of course, the smallest function value. So now let's, from on this step here, you get a system of equation. Here we have f sub x is equal to lambda g sub x. Then f sub y is equal to lambda g sub y. Then f sub z is equal to lambda g sub z. But sometimes we just have two variables. Okay, now let's look at an example. So here, the example is find the maximum and the minimum of your function given by just xy, subject to, say, along the line x squared over 8 plus y squared over 2 is equal to 1. Okay, so solution. So the objective function is f of xy. This is just xy. And then the constraint is x squared over 8 plus y squared over 2 is equal to 1. Now, we will get the f sub x is equal to lambda g sub x. This implies that what's the partial derivative of xy with respect to x, so y. And then with respect to x, we get um, um, 2x over 8 times lambda. So this is just y is equal to lambda x over 4. This is your equation. And then f sub y, you get lambda g sub y. So this means the partial derivative with respect to y of xy is just x, and then we get 2, and then 2y over 2 times lambda. That means x is equal to lambda times y. So we have a system of equations. So y is equal to lambda x is equal to lambda y, and then the third equation is x squared over 8 plus y squared over 2 is equal to 1. So this is now your, here we get to solve for x, y solution to this system. So because this is not linear, you can not put it in a matrix. So the standard way to do this is to solve for, as I will illustrate below. So first, let me label this equation 1, equation 2, and then equation 3. So from your equation 1, you get lambda is equal to y over x. Okay, I have a mistake here. This is over 4. So from equation 2, we get lambda is equal to x over y. So here, x over y. Label this as equation 4. So let us put different colors to our equations. So this is equation 4. Now, if we will substitute these are this value to our equation 1. So let's do that. So substitute 4 to equation 1. So get y is equal to 1/4 x times x over y. So this means that we get y is equal to x squared over 4y squared. 4y. That means y squared is equal to 1/4 x squared. Okay? All right. Now, we will label this as equation 5. Let's do the different color. And then the next step is to substitute your equation 5 to equation 3. Okay? So y squared, we will substitute this with x squared over 4. So x squared over 8 plus 1/2. What's our y squared? So it's just x squared over 4 is equal to 1. In this case, we get x squared over 8 plus x squared over 8 is equal to 1. So we have 2x squared over 8 is equal to 1. That means we get x squared is equal to, here we get 1, we get 4, and then multiply above, we get x squared is equal to 4. That means your x is equal to plus 4 and minus 4. This is our x, plus or minus square root of 4. So this one is, okay, this is equal to plus or minus positive 2. All right, that's it. So now we have two values for x. When x is equal to positive 2, your y will be, what's y? Y is we will substitute. So 2 squared over 8 plus y squared over 2 is equal to 1. So here, this one equation, this equation here. And that means your, this one is equal to 1 minus 1 is y squared over 2. This means that y squared is equal to 1/2 times 2. So here we get y squared is equal to plus or minus 1. Okay, so we get critical points when x is equal to 2. Here we get the points in this constraint we get 2 and positive 1, and also 2 and negative 1. So we will list this down. Now, what about when x is equal to negative 2? In the same manner, we get negative 2 squared over 8 plus y squared over 2 is equal to 1. Notice that they are the same, so y squared over 2 is just 1/2. And then y squared here is just 1, and then y is equal to positive and negative 1. So in this case, we get critical point negative 2, 1, and negative 2, negative 1. All right. we are now ready to inspect whether those at what happens at those critical points. So let us list them down. So here we get x, y, the critical points, and then the function given by x, y, and then we have the remark. So first we get 2, 1, and then 2, -1. And here we have -2, 1, and here we have -2, -1. So here the function is 2. This is -2. This is -2, and then this is +2. So the remark here is the maximum because this is the greatest. This is the minimum value. This is the minimum value 2. And then this is the maximum value. So f here has maximum value 2 at points 2, 1, and -2, -1, and f has minimum value given by -2 at points -2, 1, and 2, -1. So that's our conclusion. All right. So I have a remark there that sometimes you will get x equal to 0 and y is equal to 0, but in that case, 0, 0 is not a critical point because the point 0, 0 is not in the equation given by the constraint, which is just this is an ellipse, so it's not the origin is not in this ellipse. So I have put that in the notes. All right, maybe I'll do one more example, a slightly shorter one. So example number 2 on Lagrange multipliers. So here is the example. The function is given by 3x plus y, and then the constraint is x squared plus y squared is equal to 10. This is your objective function, and then this is your constraint equation or constraint. So what we want is find the maximum and minimum value of f given constraint, the given constraint. So solution. So first we get the gradient of f is equal to the lambda times gradient of g. So here the partial derivative with respect to x is 3, and then here we get lambda times 2x. So partial derivative of this with respect to x is just 3. With respect to actually we can write this as, we will write this as follows: minus 10 is equal to 0. So derivative of 10 is just 0. So that's it. Now, with respect to y, we get to 1 is just lambda times 2y. And then the third equation is the constraint. You can write this as x squared plus y squared minus 10 is equal to 0, or just the original one, x squared plus y squared is equal to 10. Doesn't matter a lot. So now first we will solve for this is just a circle. So this is a bounded curve. What does it mean to be a bounded curve? So if you have this equation, this is a circle, that means you can bound this by bigger circle. By bigger circle. That's what it means to be bounded. For example, in 3D, it can be enclosed by a bigger sphere. That's what I mean. So also, the equation above here, the equation above, let me put this as a remark. Equation above, we have x squared over, what's that? X squared over 8 plus y squared over 2 is equal to 1. This is also bounded. This is an ellipse. So if we get an ellipse, here, an ellipse looks like this. And then we can bound this with a bigger circle. So that's it. All right, let's continue. Now, solve for lambda. So equation 1, equation 2, and then let me write this as equation 3. So solving for a lambda from 1 and 2, our lambda is 3 halves, then x here. This is also equal to 1 over 2y. So we have y's in the denominator, so that means we can, of course, our 0, 0 is not in the circle, so it's just the outer, the boundary on the circle. So this means that, okay, 3y is equal to x. So we cross multiply. So here we will cancel this and then put this x here and then this y here. 3y is equal to x. We get this equation. So we will label this as equation number 4. Okay. And then if we substitute 4 to equation number 3. So here our equation number 3 is this. So what do we get? So x is 3y. So 3y squared plus y squared is minus 10 is equal to 0. So we get 9y squared plus y squared is equal to 10. So 10y squared is equal to 10. In this case, we get y squared is equal to 10 over 10. This is 1. And this is both, y squared is equal to 1. That means y is either positive or negative 1. So we have this. So we will solve the value of x when y is equal to 1. So when y is equal to positive 1, we get x is equal to 3 times y, 3 times 1. So this is 3. So our one critical point is 3, 1. Now, if we get y is negative 1, then x is equal to 3 times negative 1. So x is negative 3. So another critical point is negative 3, negative 1. Okay. Now we are ready to make our table. So we get xy, our critical point, the function given by 3x plus y, and then we will put the remark here. Okay, the xy, we have only 2. So here we get 3, 1, and the other one is negative 3, negative 1. So here for 3, 1, this is 3 times 3 plus 1. So we get 3 times 3 plus 1 is 10. And then the other one is 3 times negative 3. And then minus 1 is just negative 10. So the bigger one is the maximum. The smaller one is the minimum. And then we conclude that f has max value 10 at 0.31 and minimum value negative 10 at -3, -1. So this is our conclusion. All right, let me emphasize why I made the remark earlier. So constraint here must be bounded for both maximum and minimum to exist. If not bounded, either only max or only min exist, or maybe both of them does not exist. So as I will show you in this final example. All right, let me write the example. The function, the objective function is x squared plus y squared, and then the constraint is given by x, y is equal to 1. So this is a hyperbola. And then the graph of this hyperbola is this. This is our x, this is our y, and then it goes like this. So if you want a bigger circle or a bigger circle, we can bound this. We can bound this hyperbola by very big circle, or no matter how big we want our circle to be. All right, sufficiently large circle. So let's do the method that we have. So of course, we want to get the extrema here. Subject the constraint. Subject to the constraint. So, okay, let's do the solution. So del f is equal to gradient times lambda of g. So in this case, we get, what's this del? So the partial derivative of f with respect to x is just 2x, and then the other one with respect to y is 2y. This is lambda. And with respect to g, we get y, then we get x. And then component-wise equate them. So 2x is equal to lambda y, and then 2y is equal to lambda x. And then the third equation is xy is equal to 1. Okay, now, we based on the graph, your xy cannot be equal to the 0, 0, because here our hyperbola doesn't pass this origin here. All right, now let's solve for lambda. So lambda is equal to 2x over y, and then this is also 2y over x. That means if we are going to remove this, we get x squared is equal to y squared. So this means that x is equal to plus or minus y. Okay? All right. But xy is equal to 1. So here, what do we get? So either both x and y, if the x times y is equal to 1, then either x equal to y equal to 1, or x equal to y equal to -1. So, and this means we get this means we get two critical points. We get critical points 1, 1, and -1, -1. So we will inspect what happens to the critical point. So let's move down here so we get a bigger space. So the critical point we get 1, 1, and then -1, -1. So here, our function value is given by, ano nga yun? X squared plus y squared. So here we get our 2, and then we get another one is 2. So here they are equal. Are they real mean or relative max? So how do we test that? So here we can take a point. We get point. So take a point xy on xy equal to 1. So what's a test point? So here, a test point. So say 1/10 and 10. This is in xy equal to 1. So because x times this point is on the curve xy is equal to 1. So look at the value. So we have 1/10 squared plus 10 squared. This is greater than our 2. This means if this is greater than our value at this point, is greater, this means that the value function value function value 2 at 1, 1 and -1, -1 is relative, is a minimum value. That's how we reason out our answer here. In fact, we can give bigger this minimum value. Of course, in fact, in this if this is your curve, this is 1, 1. So here is occurs here, and then in fact this the function at 1, 1, and then the function at -1, -1, they are equal to 2, and this gives you the minimum value of the function given the constraint. So in this case, we have a constraint equation and we have a function. We only get the minimum value. We don't get maximum value because in fact, if you increase where x going to positive infinity, your y goes to 0, then x squared plus y squared goes to positive infinity, so no max value. So that's what I'm trying to point out, that if you have a non-bounded function, you are not guaranteed the existence of both the minimum and the maximum value. So I think that ends my lecture here on Lagrange multiplier, and then this is the end. On the meeting after the Holy Week, we get some practice exercise and sit work on this. So I think I'll end the recording now.